All right, good morning, chemists. We'll get started now. Is my microphone on? All right, so plan is for today is to continue on with chapter 16. We're going to finish all of the midterm 2 material for chapter 16, so the first half, and then jump right into midterm 3 material. My plan is to slowly finish chapter 16 next week, but also incorporate chapter 14, 15 review as well for the preparation of your midterm next Friday. Announcement that all 4 practice exams are now posted in the preparations page. So this includes the department exams. My paper versions are already posted, but I was able to post those 2 department practice exams as well. And so today we will cover all the material that is on midterm 2. So keep that in mind during your studies this weekend. You have everything at your disposal. It's just up to you to use it. All right. Okay, so let's get back into it. On Tuesday, we jumped into pH calculations. So numerically calculating is a solution acidic or basic. For the most part, pH plus POH equals 14, but only when? At 25 degrees Celsius. Yeah, if we're at any other temperature, KW is different. So the calculation is a little bit different. So true or false? Neutral water is always pH 7. True or false? False, right? It's only pH 7 at 25 degrees Celsius. At any other temperature, it's not 7 degrees. Actually, we just calculated it. Body temperature, physiological like body temperature is 37 degrees Celsius. We just did this in office hours, and I was curious. At 37 degrees Celsius, KW is different. It's a different value. We calculated it. Neutral water is actually a pH of 6.8 at 37 degrees Celsius. Yeah. So the point where water is neutral is different at our body temperatures because it's different. Our bodies are slightly basic. Our pH is around 7.3 for your reference. Anyway, okay, so we did all the numerical stuff. Let's jump into ways to categorize acids and bases. So we talked about Arrhenius acid-base theory. This is the most rough categorization scheme we use for acids and bases, and it actually doesn't always work. But this is what we learned in 1210. But as you have seen, that I am trying to unteach you a lot of stuff that we just taught in 1210 because it was easier, and one of those was Arrhenius acid-base theory, where we categorized acids simply as, okay, if there's an H plus present, it's an acid, and we name it as an acid, versus if a substance produces hydroxide in water, then that's a base. And that's essentially what Arrhenius acid-base theory is. Is there an H plus or is there an OH minus present when you dissolve it in water? That's what distinguishes it as an acid or base. And the reason this happened is because these conclusions were made solely on observations. If a solution produces H+, it'll react with zinc by making bubbles. But if it doesn't make bubbles, then it's not an acid. Versus if you have a solution that has hydroxide present, it will make a solid when mixed with magnesium 2+ cation. It makes a solid. And so if that's not present, then you won't see that observation. So this was solely based upon observations. It's the least useful of our definitions of acid-base theory. So we left off here at Bronson-Lowry acid-base theory, which is probably the most common one you're going to use. And honestly, if you're going to remember anything from this chapter for organic chemistry, it's this idea, that acids and bases donate and accept protons. Protons is an H+. An H+ is a proton. So we're oftentimes looking at how protons are moving in a chemical reaction. All right, so if there's anything you take away from this slide, it's that an H+ is a proton. So a Lewis acid is a substance that has the ability to donate that proton. So HCl can do that. HCl can donate that H+ to a water molecule to make hydronium ion, and then that can go ahead and you can calculate the pH or whatever, right? So that's a Bronson-Lowry acid. If you're just taking definitions from this slide, just memorize. Bronsted lauric acid is a proton donor. Proton donor. Versus a Bronsted lauric base is a proton acceptor. All right. So I always like remember hydroxide. Hydroxide wants an H+, so it's going to accept an H+ from an acid, and that's exactly what happens here. Here in our Bronsted lauric acid, H+ is being donated, but in a Bronsted lauric base, hydroxide is accepting an H+ to be neutralized into water. All right? Okay, so Bronsted lauric acid base theory is more robust. It actually requires us to know what we're actually working with. So the actual formulas or the chemical, like the particle diagrams, how the bonds are being made and broken, is how we notice is a proton being accepted or donated here. So I have a reaction of the strong acid, nitric acid, and I'm representing it 3 different ways, and I want us to be mindful of Bronsted lauric theory. We're looking at how hydrogen or protons are moving in this reaction. I know that nitric acid is an acid. Why do I know that? Because it's literally in its name, all right? Don't think about it too hard, okay? It's nitric acid. So if nitric acid acts like an acid, a Bronsted lauric acid, it's going to do what to its proton? Donate it. So let's see what happens here. So we have the same reaction written 3 times. Nitric acid is here, and we're going to dissolve it in water. What happens? So if you kind of inspect what is happening on the reactants versus the product side, in this first picture, I see that H+ is breaking off of nitrate, and it's attaching itself to water. All right? So we see nitric acid is donating, all right, is the source of the H+, and water is accepting that H+, right? So when we write it out with formulas, it's a little bit harder to see. So let's look at the actual particle diagram here, where the bonds are. So we see in the particle diagram, here we have nitric acid. There is the acidic proton that's coming off. Here, this proton is actually making a new bond with the water molecule. And so you see on the product side, here's that new bond that is formed, right? And there's that original, that H+ that used to be on nitric acid. We're breaking the bond on nitric acid. It's being donated to water, all right? So if nitric acid is donating the H+, it makes nitric acid the what? The Bronsted lauric acid. Very good. Then what is water doing? Water is doing what to a proton? It's accepting a proton. So in this example, water is actually acting as a base. Yeah, since it's accepting that proton. All right. So yeah, we see that there. And then the last picture also shows the same thing, that here's that proton. We're breaking this bond. And that proton is making a new bond with water, and you see that right there. All right, so here we have our H+ donor, or our Bronsted lauric acid, and then here we have our H+ acceptor. This is our Bronsted lauric base. All right, and so you see here, nitric acid is an acid. It makes H+ into solution, but remember, as chemists, we're kind of lazy, and we should understand H+ does not exist. H+ in a water solution is always attached to a water molecule all the time. So H+ doesn't exist. It actually exists as hydronium ion. All right. So the idea here is that HCl doesn't just like dissociate into a cation and an anion. That H+ is always attached to a water, but chemists are lazy and we don't like to write H3O+. We'll just write H+ and know that there's always a water molecule attached there. All right, so just keep that in mind. All right, so that is Bronsted lauric acid base theory. We're thinking about protons moving. All right, so let's talk about the last theory, and this one is the most general, it's the most robust. And what you'll see here is in our 3 theories, they all follow the same thing. It's all of our Arrhenius acids are also Bronsted lauric acids, and what we'll find here are also Lewis acids. It's just different ways of thinking about it. So in Bronsted-Lowry acid-base theory, we looked at protons moving. In Lewis acid-base theory, we're looking at electrons moving instead, all right? But our answers are all still going to be the same, but we're thinking about electrons in the context of electrons. So a Lewis acid is a substance that is an electron acceptor. It accepts electrons. A Lewis base is a compound that donates electrons. So different, because we're inspecting electrons. So let me just show you a generic acid-base reaction, but I'll show you in a little bit that Lewis acid-base theory is actually the most general of them all, and we can apply this terminology to not just acid-base reactions, other reactions as well. So let's look at this generic acid-base reaction. H plus is a what? Acid. OH minus is a base. Good. And so hopefully you just recognize that from like our Arrhenius definitions. But now let's look at it through the lens of Lewis instead. Let's think about how electrons are moving. So, you know, we write it like this in Chemistry 1210 when we did neutralizations, but recognize that there's also lone pairs on this oxygen on hydroxide, and that's very important. All right? So what's happening in this reaction, if we think about it in terms of electrons and Lewis, if this was Bronsted-Lowry acid-base theory, we would think, oh, that proton is donated to hydroxide. But that's not what Lewis says. Lewis says, no, let's think about how electrons are moving. Hydroxide is donating electrons to H plus to make a new chemical bond. So there's 2 electrons in that lone pair on hydroxide. And that is what's making the new chemical bond in the water molecule that's produced in the neutralization reaction. So let me show you it again here. Down here, I have hydroxide. These electrons in that lone pair are donating into hydrogen. And those 2 pink electrons are actually the 2 electrons that are in this chemical bond in water. All right. So this is what Lewis says. We're inspecting electrons. All right, so you told me that H plus is the acid and hydroxide is the base. So let's go back to this definition. Lewis bases donate electrons. So of these 2 species, which one's donating electrons? Hydroxide. So that makes hydroxide what? The Lewis base. And that makes H plus the Lewis acid. Lewis bases donate electrons. Acids, Lewis acids, accept electrons. And see how our definitions are still the exact same? Hydroxide is still a base, H plus is still an acid, it's just we're thinking about it in terms of electrons now and the bonds that are being made. Right, but it's important to know the Lewis structures and how electrons are moving, bonds are being made and stuff. Okay, so here it was like clear that H plus was gonna be the acid, hydroxide was gonna be the base. So let's look at an example where it's not super clear. All right, which one's the acid and which one's the base? So here, I have it already defined for us. You might have come to the conclusion that ammonia is a Lewis base, but BF3 being a Lewis acid, BF3, that's an acid? Do you see any hydrogens at all on that? Yeah, so would Arrhenius think that BF3 is an acid? No, there's no hydrogens. So this is why Lewis theory is much more robust and general for us to use these acid-base terminologies. But let's use our definitions, all right? So what's happening here is that the lone pair on ammonia, the nitrogen on ammonia, is donating its electrons to boron to make a new chemical bond between nitrogen and boron. So the 2 electrons that I highlighted here, that lone pair, are now in the chemical bond between nitrogen and boron. So what is that nitrogen doing to its electrons? Donating them. So it makes it a Lewis base. Perfect. And that boron is doing what to the electrons? Accepting. So it makes it the Lewis acid. And does that match, you know, the things here? Yes. And see how Lewis acid-base theory is more general, because just looking at BF3, I would have no idea that that's an acid unless I used Lewis acid-base theory. All right. So Lewis acid-base theory always works, always, even when H plus isn't like totally present. But for the most part in this class, we will be thinking about Bronsted-Lowry acid-base theory is probably our go-to. For this class, the remainder of this these chapters and probably for organic chemistry too. Okay, so there we go. So let's do some examples and let's just do the last two, Bronsted-Lowry acid bases, Lewis acid bases, for these two examples, all right? Because I think looking at these, the Arrhenius acids and bases are pretty clear to see, like, yeah, that's an acid, that's a base, ammonia is a base for Arrhenius acid base theory, but let's think about it in the context of protons moving versus electrons moving for our other two theories, our more robust theories. So let's look at this. Okay, so let's do Bronsted-Lowry acid base theory first. So let's look at our reactants. We have HCl and sodium hydroxide. Look to the reactant side and product side and think about what's changing. HCl is doing what? This is basically just a, double displacement reaction, right? HCl is doing what to its proton? It's donating it. So if we think about Bronsted-Lowry acid base theory, it makes HCl the Bronsted-Lowry acid or base? Acid, yes, it makes it the Bronsted-Lowry acid because your proton, so your H plus is being donated in this reaction. All right, so if HCl is the acid, that means sodium hydroxide must be the Bronsted-Lowry base. But what is happening in that reaction that is also consistent with it? It is not donating an a proton, but it is accepting it. Yes, accepting. So see how all of these things work out with one another. We already know sodium hydroxide is a base, but it's also a Bronsted-Lowry base because it's accepting that proton. All right, so let's look at it in terms of Lewis. All right, Lewis. All right, for Lewis acid base theory, what are we inspecting? Electrons instead. So what might be useful is if we draw some structures. So we have H plus over here, and then we have hydroxide over here. And do remember those lone pairs. All right, and so when we think about water being formed, we made this new bond in that water molecule. So when thinking about electrons moving, H plus is our electron acceptor, because actually H plus has no electrons in it. It's only going to ever accept electrons. So it's just a proton. So what's happening is that hydroxide is donating into that H plus is accepting electrons, and that is consistent with a Lewis acid. Versus hydroxide, it is donating electrons, so that makes it the Lewis base. And see how they're all acids. HCl is always an acid. Hydroxide is always a base. It's just different ways of thinking about it. So let's do one more, again, with Lewis acid base theory. So let's do Bronsted-Lowry and then Lewis. Okay, Bronsted-Lowry, we look at what? Protons. So look and see what bonds are being formed, right? Here's that red highlighted proton. That's what's moving here. All right, and so if we look to the products to the reactant side, I see that proton is going from water to ammonium to the nitrogen. It's making a new bond. So what's happening is that we're like breaking this bond, and we're making a new bond with the ammonia. So what is donating the proton? Water or ammonia? Water is actually donating the proton. So H plus is being donated because that's where the bond is being broken. So that makes water the what? Lewis acid. Weird. Interesting. Versus ammonia, it's actually doing the proton accepting. So it's accepting that proton because that's where the new bond is being made. So that makes it the Lewis base. Or sorry, not Lewis base. Sorry. Bronsted-Lowry acid. Bronsted-Lowry base. There we go. Yes, because we're looking at protons moving. Okay. All right, and that again will be important in organic chemistry and us looking at conjugates in a minute. Yeah. Okay, so now let's look at Lewis. In my humble opinion, I like Lewis acid base theory, but that's because I love electrons. And I understand electrons moving, but anyway, we can think about this in terms of where the bond's being made, what's being broken, and that's Lewis acid-base theory. So let's inspect what's happening. We're creating this new bond. That chemical bond had to come from somewhere. Those two electrons were the lone pair that were on nitrogen. All right, so that makes nitrogen the what? Lewis? What's it doing with its electrons? Donating it into the bond. So that makes ammonia the Lewis base. Lewis base. Lewis bases donate electrons. Lewis acids accept electrons. Is water accepting that electron? Yes, the H plus is. So that would make it the Lewis acid, right? Because it is accepting electrons. Okay, and so those are our definitions. This is more similar to how an exam question will be worded. You know, what's the Bronsted-Lowry acid? What's the Bronsted-Lowry base? Not just regurgitating a definition, but actually inspecting what bonds are being made and broken and applying that idea. Okay, so let's look at this last example. So when we think about this reaction in the forward direction, all right, ammonia is taking or is accepting that proton. So it's acting like a base. But once we form that bond, we make this compound. This is called ammonium cation. All right, so this substance has an extra hydrogen on it, an extra proton, and it can actually act as an acid. All right, so once a base acts as a base, it produces an acid. Or if we think about this, when an acid acts like an acid, the product is a base. Once you've spent your acid or once you've spent your base, you make the other thing. And so this is the idea of conjugates, that we're going to be looking at weak acids and weak bases here very soon. And so conjugates will be very important, where it's basically conjugates is the product that's made once your acid acts like an acid or your base acts like a base. It's the product that's left over after that reaction happens. So when you think about this, when an acid acts like an acid, and acids do what? Let's go back to Bronsted-Lowry acid-base theory. Acids donate. You know, you donate a proton. Or you can think you remove a proton from that compound, all right? What is left over on the product side is your conjugate base. So HA is just a generic acid. But once you've removed that proton and spent the acid portion, what you're left over, your change essentially, is a base, and we call that a conjugate base. All right, so these two substances, HA and A-, they come from the same anion species, but they differ by just one proton. All right, so acids donate protons, make their conjugate bases. That one most students can get. It's the base one that's a little bit more difficult. Bases, on the other hand, after they behave like bases, they actually make what's called a conjugate acid. All right, so a conjugate acid is made after a base acts like a base. Bases accept protons. All right, so where's that proton coming from for a base to be a base? It's actually coming from water. Remember, water is HOH. So what's happening is that base is grabbing a proton from water, leaving behind that hydroxide. And it's that presence of a hydroxide that makes this substance basic. All right, so here a base is reacting with water to make a conjugate acid. So bases are basic, but conjugate acids of bases are actually acidic. And so we'll be looking at this kind of balancing act of both sides of the equilibrium here very soon. So here's, I showed generic equations, but let me show you it again here in this example. Ammonia is our base. It's a base. Once it acts like a base, you're actually accepting a proton. You add an H plus to its formula, and you create its conjugate acid form. So NH4 plus actually behaves as an acid, right? On the other hand, you know, ammonia is a base, but what's also reacting is water. Water here in this example is acting like an acid because it's giving up a proton. It's doing the proton donating. And what you see what's left over after our acid acts as an acid is you're left over with its conjugate base. Or sorry, conjugate base. So you see here we have a base and an acid, and on the other side we have the conjugates of those forms, where the conjugate of a base is an acid, but the conjugate of an acid is actually a base, right, in terms of donating. Okay, so let's go through this. How do we get conjugates? We need things to act as acids or things to act as bases. So we just have to be careful of, are we removing or adding an H+? So not only do we add or remove the hydrogen part, but we also have to be cognizant of the charge. Conjugates only ever differ by one proton, one. Okay, so if I ask you to make a conjugate of something, you're either adding a proton or removing a proton, but we just need to know which one. And so let me walk you through it. So in this question, I'm asking you, what is the conjugate base of these things? All right, so the conjugate base is the product. So that means all these things that are listed, these are acids. All right, so when an acid acts like an acid, you make a base as a product. All right, so what are we going to do? To make a conjugate base, are we going to add or remove a proton from these things? We're going to remove, because these things are acids, all right? So make these acids act like acids and remove a proton. So that's what we're going to do. Let's remove a proton, or we're essentially donating these protons to something else, all right? So what we're doing is removing a proton. We're only removing one proton. And again, be cognizant of the charge. So when we remove a proton from HCl, what do we get? Cl minus, and it's aqueous. All of this is aqueous. Okay. HCN, what do we get? Cn minus. Okay, H2SO4. HSO4 minus. So remember, remove one proton at a time. All right, and then here's the second, so the conjugate we just made, we see, oh, there's another proton that can be donated. That's exactly what happens. This thing is still an acid. All right, and we can go ahead and remove one more proton, and that's how we get SO4 2 minus. Yes. But can SO4 2 minus continue to act like an acid? Nope. How do you know? No more hydrogens. Yes. So SO4 2 minus is most likely a base. Yes, because it's the conjugate of this acid. All right, keep going. Ammonium. What do I get? Just NH3. There's its conjugate base. Water becomes OH minus, and then hydronium becomes water. Perfect. So these are all of these are bases, conjugate bases of these acids. We remove those protons. All of these differ by just one proton. Okay, let's build the conjugate acid of these things. All right, so when these things, how we form a conjugate acid is we take a base and we make it behave like a base by accepting a proton. And that's how we make a conjugate acid. Right? These things are bases. Bronsted-Lowry bases accept protons. So let's accept protons to make the conjugate acid. So what we're doing in practice, what we're doing is not removing a proton, but what are we doing? We are adding a proton to these formulas. So again, you add the H, but you also check the charge. So we're actually just undoing what we just did. When we add a proton to chloride, what do we get? HCl. So chloride is the base, HCl is the conjugate acid. Is HCl an acid? Yes, it is. So that's consistent with that. All right, then we get HCN. Again, we're adding one H+. Ammonia, what do we get? NH4+, yep. Then this guy, H2SO4, yep. The neutral one, SO4 2 minus, what do we get? HSO4 minus, perfect. Hydroxide becomes water, and water becomes H3O, perfect. All right, good. Okay, so that's not bad. where we're just removing or adding protons depending if, we want the conjugate acid or base. So we just have to be careful with our language. Is our thing acting as an acid or base? And we're always falling back to Bronsted-Lowry acid-base theory, where protons are accepted for bases or donated for acids. All right, so that kind of question's fairly easy. So now let me show you what the department loves to do. And it's use this table, but I have to show the table in increments. All right, the whole table is this. The department loves this table. I've looked at the past 3 exams. Every exam has had this table in it somewhere. So let's go through this table. All right, and so what this table shows us is relative acid-base strengths of the acid and its conjugate base. Remember, every acid has a conjugate base. Every base has a conjugate acid. And there's this rule about it, and let me talk about it. So if there's anything you walk away from in this chapter, in this section, is that the stronger an acid is, when you make its conjugate, that conjugate is really crappy. All right? So the stronger your acid is, the weaker your conjugate base is in basicity. Right? It's like our acids and bases, 2 conjugates. You can't be good at 2 things. You either are really good at being an acid or you're really good at being a base, and that's it. Or you can just be mediocre at both. All right? It's kind of like real life. It's like, I feel like I'm pretty good at teaching chemistry. Oh, but biology, I can't teach that. All right, so let's talk about this chart. Here are some examples of strong acids. Strong acids fully ionize in water. So when I draw out the reaction of HCl acting as an acid, HCl, arrow, H plus, Cl minus, what kind of arrow, note what kind of arrow am I using? Is this the right kind of arrow I should be using for HCl? Or should I be using this kind of arrow? No, why don't I want to use the equilibrium arrow? Yeah, HCl is a strong acid. Okay, so I'm using the fully forward direction arrow because this isn't an equilibrium. So based upon the arrow we're using, is this reaction reversible? No, it's not. Only the forward reaction happens. The reverse reaction does not happen. HCl is an acid. So that makes chloride its what? Conjugate base. So if I'm telling you this backwards reaction never happens, that means that chloride is not a base at all. If the backwards reaction does not happen, it's actually what we call a neutral. I have to specify a pH neutral anion or salt. All right, chloride, nitrate, all of these are pH neutral. You put those in water, pH stays at 7 as long as we're at 25 degrees Celsius. All right, where things change is when we aren't working with strong stuff. All right, so HCl dissolves in water, HCl is acidic, but chloride is pH neutral. It is not a base, it's nothing, essentially. All right, and the reason is because the stronger the acid, the weaker its conjugate base. So HCl is so strong that its conjugate base is nothing. It does nothing. Okay, all right, so no, it's not reversible. Perfect. All right. So those are strong acids. So yeah, all those strong acids have really, really poor bases as their conjugate base. All right, so let's look at other substances. So let's expand the table. Okay, so if we go down in this table, what we're doing is decreasing the acidity of these substances. So when you think of just like a generic acid, HA goes to H plus and A minus. It's the presence of H plus that we use to calculate the pH, right? So for a strong acid, HCl, all of that HCl becomes H plus, and that's why the pH is so low. That's why it's so acidic. But for weak acids, do weak acids fully ionize? No, they use K expressions, right? We have to use a K expression to talk about the equilibrium. Both the reactants and product sides exist at the same time for weak acid or weak base. So for any of these weak acids, we don't fully ionize to H+. So our pHs are not as low as a strong acid because these are weak acids. They're still acidic. They just don't make as much acid as these strong acids. They only partially dissociate in water, so we have to use those equilibrium arrows. All right? So if we read this table, HSO4 minus is the strongest of the strongest of the weak acids, but HPO4 2 minus is still a weak acid, but it's just not as strong of a weak acid. All right, so these ones will have higher pHs than these ones that are stronger weak acids. They ionize more. All right, so these are the acids. And then here are their conjugate bases. So the rule is, the opposite is true too. I mentioned the stronger the acid, the weaker, the crappier its conjugate base. But that also means the weaker the acid, the stronger its conjugate base, right? You can't be good at two things. You're either really good at one thing and crappy at something else, or you can be mediocre at both things. And that's kind of what weak acids do here. So the weaker you are as an acid, the stronger your conjugate base is. So this is how we read this table. All of these strong weak acids actually have very poor conjugate bases, versus the really crappy weak acids on the bottom here have very good conjugate bases. Okay, so let's see if we can't read this table. Here we have the acids, here we have the base form. So let's name an acid that's stronger than HF. So locate HF right here. Name a weak acid that's stronger than HF. So what do we want to look at, above or below? Below? Above. Yeah, I don't know. Or maybe my ears don't work. So I'm just going to say H3PO4, right? We're looking for above, because that's how we read the table, right? So that's for HF. HF is an acid. But now PO4 3 minus, that's a base. So do we want to look at the acid side? Nope, we want to look at the base side. Yeah, we want to look at the base side. So we want to look for a substance, above or below phosphate? Where's phosphate? It's right there. Below, yeah, we want to look below. And so there's only one substance below phosphate in this table because I've cut it off, and that is hydroxide. Is the only thing that is stronger on this table, a stronger base than phosphate ion. All right? So that's how we read this table. Bases decrease going down, acid strength increases going up. And so we see kind of this counterintuitive idea that's happening. Okay. So let's, last idea here, right? Strong acids have what? Good or bad conjugate bases? Bad. Weak acids, they have like okay acid strength, so they'll have okay base strength of their conjugate bases. But the rule is weaker the weak acid, stronger the conjugate base. Versus you can have a substance that's such a poor acid, a very, very, very poor acid, that if you make a conjugate base where if you force and take one of its protons off, the thing that's made is actually a really, really, really good base because it wants that proton back, right? So if you have a substance that's really crappy at being an acid, its conjugate is going to be a really fantastic base. All right, so again, our definitions still work. The idea that stronger something is, the weaker its conjugate is. Or if something is so weak, its conjugate is going to be really strong. And then all of the ideas between. All right. So yeah, conjugates of anything that's a non-acid is going to be a very, very, very strong base. These things over here, and we rarely work with them, they're very strong bases because they're going to just accept any H plus that's around it. Right? It's just going to take H plus from anything like water. And so they're really, really good bases. All right, so that's the table. Now let's do exam type questions. And I'll try to make them harder. All right, so we're going to use the same table. And the idea is the stronger the acid, weaker the basicity of its conjugate. So I'm giving you the full table here. So I'm going to point out that answering these two questions, it's a lot easier when we give you the full table. But I'll teach you how to answer the question if I only give you half the table. So let's do it the way with the full table first. So tell me, which is the stronger acid, H2S or NH4 plus? So we want to look at what, the red or the blue? The reds, because those are the acids. So let's look at the reds, and we are going to look for the acid that's what? At the top. Yeah, and so which one is that? H2S, perfect. All right, so then which one is the stronger base? Here we go. Here are our bases. Are we going to look at the red or are we going to look at the blue? Blue. And so we're going to look for the substance on the bottom. So which one is it? NH3, perfect. Okay. If that was an exam question, you would answer that in like 30 seconds, right? But here's the thing. It was easy because I gave you the full table. So let's see if we can't answer if I only give you half the table. All right, so the first question, these are acids, right? So it would be super easy to answer this question if I gave you the acid strength table, right? But what if I don't give it to you? What if I only give you the bases? So let me just cross this out. You can still answer it, I promise. All right? So let's answer the first one. Which one is the stronger acid? But I only give you the bases. Right? So remember our relationship. Stronger the acid, crappier, weaker the base. So since I give you the bases, but I'm asking you the acids, the strongest acid is also going to have the what base? Weakest base. So we kind of have to just change and interpret the question, all right? The stronger acid is going to have the weaker conjugate base. So I want to answer it this way because I'm giving you bases in the table. All right, but now here's the hard part. I give you acids. Now you need to figure out what substance you need to look at. You need to actually figure out what the conjugate base is for these things. So how do we make a conjugate base from an acid? We remove a proton. So remove a proton from H2S. What do you get? HS minus. And then from ammonium, you get NH3. So these are the two substances you want to look up on this base table because that's what's given. All right, so I'll find those. Where are they? They are right there and there. Okay, but we want the stronger acid. So we want the thing that's the weaker base. And so which one is that? HS minus. So that means that H2S is the stronger acid. Is that what we said earlier? Yes, it was. Yes, it was. Okay. Do the other one too? Okay, we'll do the other one. Okay, so let me just erase that here, but then I got to move this over here. Okay, so now let's answer this other one. Which one's the stronger base? But I'm going to be evil, and I'm not going to give you the base table, because then that would just be too easy. I'm going to give you the acid table instead. All right? So remember our idea of complementary acid bases. Which one is the stronger base? But I give you acid information. So something that is a strong base is going to have what kind of conjugate acid? Very weak. So we're actually looking for the weak conjugate acid. And I want to interpret it that way because that's what's given. But unfortunately, these substances, they're bases. So I need to make the conjugate acid so I can locate them on the table. So what is the conjugate acid of HS minus? H2S. So we add a proton. And then for ammonia, it's NH4 plus. So those are the things you want to look for on the table. So if we look for it here and then there, stronger base has the weaker conjugate acid. So which of these is the weaker acid? Ammonium. So that means ammonia is the stronger base. And is that what we said earlier? It was, yes. All right. And so doing it this way makes it infinitely harder. Okay, so let's do one more that is also kind of tricky. Okay, give myself room here. All right, so using the same table, this time I'm going to give you the whole table. I'm going to mix an acid and a base together, and I want you to predict which side wins. All right, we're mixing an acid and a base together, and I want to know at equilibrium, am I going to find more product or am I going to find more reactant at equilibrium? This one's tricky. When we're mixing two things and we're comparing two things on the table, this is the strategy you want to use. Recognize that anything that's strong, a strong acid, a strong base, ionizes more, produces more product, has, a like completely forward arrow. Strong acids, strong bases, completely full arrow. So when trying to answer this question, I like to look for the strongest acid and strongest base. They will appear on one side of the reaction. And recognize that the strong things always push to the other side. So if you locate the strong acid-base pair, know that the equilibrium will lie on the opposite side because strong things always push to the other side. All right, so here's an example. All right, so this one. The first one, we mix HCl, ammonia, and we make those products. So I note here that HCl is what kind of acid? Strong acid. Ammonia is a weak base, all right? But HCl, it's the strongest acid. If you compare HCl to ammonium, ammonium is the conjugate acid of a weak base, so NH4 plus is a weak acid. Strong acids beat weak acids. So this reaction, so I like to think HCl wins, so it pushes the reaction to the right side of the equilibrium. All right, so if you were to make this mixture and look at it, you would find mostly chloride and ammonium present in that solution. You won't find any HCl. All right, so that's the idea. Look for the strongest acid or base, and the strongest thing always wins. So that was for the acids. So I compared the acids here, HCl and ammonium. Those were the two acids. That means ammonia and chloride are the bases. So ammonia is what kind of base? A weak base, all right? And then chloride is the conjugate of HCl. But is chloride a base at all? It is not. It is a pH neutral salt. So ammonia wins here in terms of basicity as well. But I always try to look for the strong things because that's just easiest for me. Right? So both of those will work. Okay, so then this one, sorry, I had a mistake in there. Even this is tricky for me. Again, look for the strongest thing, either the acid or the base, and then that pushes to the other side. So we have hydronium and then fluoride combining. So to me, hydronium is the acid. Fluoride has to be the base because fluoride has no protons. So what we want to do is compare the two acids. So H3O plus versus HF. I need to know which one of those acids are stronger. And so you locate them on the table. H3O plus is right here, while HF is right here. All right? So H3O plus wins. So it pushes the reaction in the forward direction. Okay? We can do it for the bases too. If these two things are the acids, then F minus and water have to be acting as bases. So let's locate them on this table. Fluoride is right here. Water is right there. Which of these is the better base? Fluoride. Fluoride is the better base, so it pushes it to the right side. All right, so both hydronium and fluoride are the better acid and base pair. So it pushes to the other side. Okay, last one. Again, let's just find the stronger acid-base pair. Okay, of these two things, H2S and ammonia, which one is the acid and which one's the base? H2S is a acid, cool, and then that means ammonia is the base. And so this is going to help us because I need to, locate the two acids and the two bases on each side. So on the product side, which thing, if you think about the reverse reaction, which one is the acid? HS minus or ammonium? Ammonium is the acid, yes. Oh, sorry, that's the wrong color. This one, all right? Ammonium is the acid because ammonia was the base, so ammonium has to be its conjugate acid, and therefore HS minus is the base. So compare the bases, compare the acids, and you want to pick the stronger side. Okay, so let's just do the acids, because I like to think about acids. H2S is right there, and ammonia is right there, or sorry, ammonium. H2S wins, so this gets pushed to the right side, right? You can do it for the bases as well. You don't actually have to do both. Once you get one, the answer comes out, but it is also consistent with, okay, ammonia and H2S, you look at those two bases on this table, it's right there and there, and you see, oh yes, ammonia is the stronger base, it pushes to the right side. All right, so that's how you do it when you mix two things. That one is inherently harder, because we're looking at two substances and you have to locate, are you working with an acid or a base? All right, okay, so that actually concludes midterm 2 material. All right, so we did the calculations, the pH scales, understood how KW fits into everything, where pH plus POH equals 14 comes from. It actually comes from KW, and the idea that that value changes with temperature. So pH plus POH equals 14 is only good at 25 degrees Celsius. Then we just looked at the conceptual things, the ways we categorize acids and bases. It's not just H plus and OH minus anymore. And we looked at conjugates and their relative strengths. All right, so I just want to reiterate for the exam, it stops right here. You will only be responsible for strong acid base calculations, like pH calculations, but still being able to navigate this table is useful. And you'll need to know that. And so what we're going to do, so what we just did is we were able to calculate pHs of strong acids and strong bases. Now we are going to calculate the pHs of weak acids and weak bases. All right, so I think reviewing these things will be helpful for your midterm because they're all related to one another, but equilibrium is going to come back, but honestly it's easier than chapter 15 in my opinion. Okay, so weak acids, oh yeah, I should point out that homework set 1 is due now. We're not going to finish the chapter, so homework set 2 is due after the midterm. But homework set 1 is due on Monday. It's for your midterm anyway. So, okay. So let's remind ourselves what equilibrium is, right? So some reactions undergo a chemical equilibrium where the forward rate is equal to the reverse rate. And weak acids are one of them. Remember we talked about strong electrolytes, weak electrolytes, non-electrolytes in 1210, and I told you, you know, when we showed the light bulbs, strong acids were bright, weak acids were dim. We just kind of said, oh, these undergo an equilibrium, both sides of the equation exist at the same time, and we left it at that. But these weak acids, they follow a chemical equilibrium. They have a double-sided arrow, so therefore they have K expressions as well. So we're going to talk about two new K expressions, Ka and Kb, where A, well, let's just go through all the Ks. Kp, what does P stand for? Pressure. That's most important for gases. Perfect. Kc stands for concentration. So things that are aqueous and gases. Gases can have concentrations too, but everything in that K expression needs to be in concentration. Ka, what do you think the A stands for? Acid, yes. So a Ka is just a Kc expression for an acid acting as an acid. Kb, what does B stand for? Base. So Kb is just a Kc expression for a base acting like a base. And that's it. So these are no different than chapter 15, but we need to be cognizant of how do acids behave and how do bases behave. So let's look at our prototypical weak acid, HF. But it's funny, it's like you'll never actually work with HF because it's like super toxic. But we talk about this as our common weak acid, and here's, you know, the reason why I use HF all the time? It's the shortest weak acid name I can write. Yeah, it's because I'm lazy. Okay, so HF acting as a weak acid, you put HF into water. All right, it's an acid, it's a proton donor, so it donates its proton to water to make hydronium. And then you make fluoride minus, that's its conjugate base. All right, but here's the thing, chemists, we are lazy and we don't like to write water. So instead of writing water and hydronium, we will replace it with just H+. And so we can simplify this HA expression as just HF splits up into H+ and F-. All right, we can simplify it. So we can write the K expression for this just like before. K expressions are always what? What? Products over reactants. Is it any different for this? No, it's not. We just have to make sure we get the right equation. We can actually use any one of these equations. They will be the exact same. So let's do the top one first. The top one, this equation, we take the two products and we divide by the reactants. So Ka for that first top expression is H3O plus times F- concentration. And then what's my reactants? HF. Do I put water in it? No, because water is a liquid. All right? Or do you want to be lazy and use the lazy way? Do the lazy way. So if you write the same K expression for the lazy way, what do you get? You literally get the same thing, but instead of H3O, you just write H+ instead. It's the same exact thing, but I want to just show you that they're the same thing. So you prove it to yourself and you don't just trust me. All right, so these are the same exact expression. Just one includes water, one doesn't. Because does H+ exist? No, it's always attached to water. But I'm lazy, so I write it this way. Okay, so there's my Ka expression. What's cool about acids is you can look up a Ka for any acid or base, but it is temperature dependent, like always. So this HF has a Ka expression, or a Ka value of like times 10 to the -4. So is this Ka a small number or a big number? Small. So of the products versus reactants, what's present more at equilibrium? Yes, it's reactants, because K is really small. All right, so you're actually not going to make a lot of H+. You're not going to make a lot of F- when you put HF into water, right? So if you don't, if you don't make a lot of H+, how is that pH affected? It's not going to be very acidic. The less H+ you make, then the less acidic that water will be. All right. Okay, so that's a weak acid. Now let's do weak bases. For weak bases, things that behave as bases, weak bases especially, when you put weak bases into water, you have to have a water molecule present, because bases are what kind of Bronsted-Lowry thing? They do what to protons? Accept protons. So I can't just write a weak base in the equilibrium. I need a water molecule there because it needs to take a proton from something. It's going to take it from water. So you see here ammonia plus water. Again, water is the proton donor in this case. I need that there. So ammonia is going to take that proton. You make ammonium. That's your conjugate acid. And then hydroxide there is the conjugate base from water. All right. So that is a Kb expression, something acting as a base. A base reacts with water, steals a proton to make hydroxide and your conjugate acid. That one is harder to get. I would practice conjugate weak bases, because it seems like acids students get right away, but the base ones always take longer. So let's get the Kb expression. It's the same as before, just products over reactants. So on the top, we have NH4 concentration times hydroxide concentration, and then what goes on the denominator? Ammonia. Anything else? Nope, water does not go in there. All right, so look, our bases make hydroxide. If we know this concentration, we can calculate POH, we can calculate pH. Or for an acid, if I know Ka and I know other concentrations, I can calculate H+ concentration to get pH, and that's exactly what we're going to do. All right. But since these use K expressions, how do we get equilibrium concentrations for K expressions? We got to use a ICE table. But thankfully for chapter 16, this chapter, it's easier than chapter 15, because we can always make an approximation. All right, so let's talk about the details of Ks. All right, so when K is when Ka is a big number, in general, you have a lot of what at equilibrium? Products. If K is a small number, you have a lot of reactants. So when will your solution be more acidic? What does acidic mean? A lot of H+. So when will your solution be acidic? When Ka is big or when Ka is small? Big, yes. Acidic, the strongest acids have large Kas. And that's what this next slide is, okay? Strong weak acids. Weak acids that are really acidic, that make a lot of H+, have large Ka values because Ka is products over reactants and H+ is a product, right? So here's a bunch of acids, and then here are their Ka values. So you see here we have chlorous acid is one of the strongest weak acids, and it has a Ka value of times 10 to the -2. So that's a pretty large number versus like acetic acid, what you and I are used to, has a Ka value of 10 to the -5. Right? So if you have a solution of chlorous acid and acetic acid, which one's going to have the lower pH? Chlorous acid, because it is the stronger acid. It has a larger Ka value. Remember, exponents 10 to the negative something, you're looking for smaller numbers because that's less times you move the decimal place, all right? So here, yeah, chlorous acid is a very strong weak acid. It's still a weak acid. It's just stronger than all of the other ones. Here, these compounds that have really, really small Kas times 10 to the -10, these are very weak acids. They basically aren't even acids at all because their Kas are so small, meaning you barely make any product. You barely make any H+ at all when you put those things in water. Okay, but remember, if there's anything you get away from 1210 and 1220, is that chemists were lazy and we don't like to write. Do you like to write scientific notation? No, it sucks. No one likes to do it. So that's why we use pH, right? The P function. pH means what? Negative log H+ concentration. POH means negative log OH concentration. P bananas means negative log banana concentration. So pKa means negative log Ka. Because what do you want to write? Do you want to write 1 times 10 to the -2 for Ka, or do you want to say pKa is 2? pKa is 2. So all of these numbers, pKa's, is just the negative logs of those Ka values. So you'll probably find those in books. Like if you look up, okay, like acetic acid acidity, you might find the pKa, right, of acetic acid because people don't want to write 1.8 times 10 to the -5 because that's annoying. But we'll write 4.74. Yes, it's 4.74. But I've memorized both, at least for acetic acid. So there's your pKa's, all right? And so Ka to pKa is negative log, but then to undo a pKa, what do you do? 10 to the negative pKa, yeah, all right? And so again, the P function just allows us to not have scientific notation. Okay, so that means a strong weak acid has a large Ka value, all right? But then that same strong weak acid is gonna have a small pKa value because of how that negative log function works, all right? Okay, so those are our Ka values, all right. So let's jump into it. Calculations involving weak acids. Remember, weak acids, they are chemical equilibrium. Oh no, is my pen dead? Come on. There we go, all right. These are weak acids. They follow chemical equilibrium just like chapter 15. Right? We just have a special K expression to use, Ka expressions, especially for acids. So let's calculate the pH of, oh no, this one's different. Okay, so let me back up a little bit. Chapter 15, I introduced ice tables. Did we always have to do the quadratic? Did we always have to use an approximation? No, only sometimes. So I differentiated ice tables. There's two different types, right? The ones where I give you the initial line. I give you a hint at the equilibrium line. I ask you to calculate Kc. Those are what I call you Sudoku, your ice table. You never have to make an approximation. Then there's the ones that I give you the initial line. I give you K. You need to determine the equilibrium line. That you may have to use an approximation, do the quadratic, right? Same thing for this chapter. All right, it's just chemical equilibrium. Honestly, it's easier because everything's a 1-to-1 ratio. So here is a type 1 ice table, but involving a weak acid. All right, so let's take a 0.1 molarity formic acid solution. It has a pH of 2.38. Calculate its Ka. This question is no different than chapter 15. The only difference is that I didn't give you the chemical equation, so you have to figure it out yourself. But thankfully, all Ka expressions are the exact same. They're the exact same that I can just write a generic one. I can just take a generic acid, HA. When HA acts as an acid, what does it become? H plus and A minus. All weak acids are going to look like that. All Ka expressions are going to look like that. All right. But in this case, formic acid, right, they write HCOOH, right? I can just replace that with HA, and it's the same thing. It doesn't matter, right? Okay, so let's write our ice table. This is Sudoku method, so we don't actually have to do an approximation. So we just have to be careful of the data that we put in, all right? So I tell you that we start with a 0.1 molarity formic acid solution. So where does that 0.1 go? In which line? Initial, yes. Under what? HA, yep. So we put 0.1 molarity there, and then how much H plus and A minus do we have? 0, perfect. Does this feel familiar? Yes, where does the reaction have to go? Forward. So what goes in the change line, left to right? Minus X, plus X, plus X. This is why acid-base equilibrium is easier, because the stoichiometry is always 1-to-1 to 1. It's easier. Okay, and now we just, do the column. So at equilibrium, we have 0.1 minus X of HA. All right, there's my hint. I didn't want to show that. And then we have H plus an X amount and A minus an X amount. All right. Then what do we do with an ice table once we get the E line? We put it into K. Yeah, so get K, but specifically, this K is Ka, but still it is H plus concentration times A minus concentration over your initial acid concentration. Or sorry, not initial, it's your HA concentration, right? The question tells you, oh no, we're trying to calculate Ka. All right? So we have expressions to go into our Ka expression, all right? But what's the one piece of information we didn't use yet? The pH. Okay, so here is the hint. And this is what makes it a type 1 Sudoku method question, is that if I give you a pH measurement, it always describes H plus concentration at equilibrium. At equilibrium. So if I tell you the pH is 2.38, you can calculate the H plus concentration at equilibrium. And in the context of that this question, that concentration is X, all right, based upon this ice table. All right, so, the question says pH is 2.38. You need to understand that any pH value is the concentration of H plus at equilibrium. So that means H plus at equilibrium is 10 to the negative 2.38 molarity. That value, I think if you calculate it, okay, 10 to the negative 2.38 is equal to 0.00417 molarity. All right? That number is X. It's X. See how the Sudoku method, there's always a hint to get part of the equilibrium line. Because now that we know X, do we know all of the equilibrium concentrations? Yes, we do, and we can plug that into the Ka expression. So that means Ka is equal to, remember it's X squared over 0.1 minus X, so it's equal to 0.00417 squared over 0.1 minus 0.00417. And then you're done. And then K is that 1.8 times 10 to the negative 4. Should we make an approximation here? No, why? But minus x is so small. Why can't we make an approximation? Do we have to? What's the point of making an approximation? To avoid doing the quadratic. If you do an approximation here, you're just being lazy. You know what x is. Just do the subtraction in the denominator. All right? Okay, so don't try to apply a approximation to anything. We only do that when we want to avoid doing the quadratic. This is just algebra. All right, good. All right, so type 1, do you ever have to use an approximation? No. When I give you I and I give you part of the equilibrium line, you never make an approximation. But when I give you initial concentration and I give you K and you have to calculate equilibrium concentrations, sometimes, yes, you do have to do an approximation. Actually, before I do this question, I forgot. I want to get on my soapbox for a second and read you this question. A student prepares this formic acid solution and found its pH to be this. Okay, so now that you all are smarter, you're more comfortable in lab. Do you feel more comfortable in lab now? Yeah, okay. Okay, so I'm going to give you some advice because you'll be scientists and communicating scientifically to one another. You don't find data. Okay, that implies that you lost it and you found it in a drawer somewhere. Give yourself more credit than that. If you're measuring the pH, you measured it, right? You determined it, you calculated it. Give yourself more credit. You don't find data, you measure it. So I don't like this. I wish it would say it was determined, the pH was determined, it was measured, anything. You don't find data. It sounds like you lost it and you opened a drawer and just found it there by accident. So give yourself a little bit more credit than that. I don't like the word found. Maybe my colleagues will disagree with me that it's not important, but I like to be careful with the language that I use. Okay, so let's move on to the type 2 question. And the reason it says that is because I got lazy and just copied the question from the textbook. So let's do a type 2 question where we may have to use the quadratic. So it's no different than chapter 15. We just got to be careful. So here, what is the pH of a acetic acid solution? And there's its Ka value. So let's get the pH first, and then we'll answer percent ionization. So when doing weak acids, we need to start with a balanced chemical equation. In chapter 15, we always gave it to you. But in chapter 16, Kas, they are always the same. They are always, we have a weak acid. It dissociates into what? H plus and A minus. That is the Ka you will use over and over and over again. In this example, it's acetic acid, but it doesn't matter. It doesn't matter. All right, so we write out our ice table and we fill this sucker in. So 0.3 goes where? Initial. So 0.3 molarity goes in the initial HA concentration. How much H plus and A minus do I have? 0. Okay, what's my change line? Minus X plus X plus X. Does this look familiar? Yes. And there's comfort in familiarity. So then at equilibrium, I have 0.3 minus X of HA, X amount of H plus, X amount of A minus. Which value is going to help me calculate pH? What do I need to get pH? I need H plus concentration, so I need to figure out what X is. Does that sound familiar? Yes. Okay. So how are we going to figure out what X is? Plug it into Ka. Ka is H plus concentration times A minus concentration over HA. Or X squared over 0.3 minus X. Does the question give you Ka? Yes. 1.8 times 10 to the negative 5. So this is no different than any other type 2. Maybe use the quadratic question from chapter 15, but just easier because everything's a 1-to-1 ratio, right? Does this require the quadratic? Yes. Do you want to do the quadratic? No. So what do you think we can do? Approximate. But let's think it through. ask yourselves, is K big or small? Small. So do we make a lot of product? No. So X is really small. So if we take 0.3 and we subtract a small number, all right, if this is really small, then we can just say that that whole thing, 0.3 minus X, is just equal to 0.3 instead. And that's why we can approximate. It's because minus X. Ka is small. We can say that minus X is going to be really small, that this can just be approximated to X squared over 0.3 equals 1.8 times 10 to the negative 5. Does that require the quadratic? No, it doesn't. Thank goodness. And so you can check for yourself using Wolfram Alpha that with and without the approximation, you get the same answer within like I think the fourth sig fig is different, the fourth one, all right? So you solve for this, calculate X, so 1.8 e negative 5 times 0.3, take the square root of that, and we get that X equals 0.00232 molarity. But that's the concentration of what? H plus, is that what we want? Yeah, we're getting closer to what we want. Yeah, so that's H plus concentration. So how do we get our answer? Negative log that. So negative log that number, and you do get a pH of 2.64. So 2 decimal places, because Ka has 2 decimal places, or 2 sig figs. See, this is no different from chapter 15. Honestly, it's easier because 99.9% of the time for weak acids and weak bases, you can approximate. You can approximate. So let's do the last question here, and that is the second part is what is its percent ionization? So we just calculated the pH. Here is the equation for percent ionization. So remember when I told you about approximations, I said typically we can approximate if X is less than 5%, all right? This is the 5% I was talking about. So how ionized is your sample? So to calculate percent ionization, we actually have all the numbers we need. We just need to plug in the right ones. Percent ionization is H plus concentration at equilibrium over your initial concentration. We were given initial concentration, it was 0.3, but H plus at equilibrium, what value is that on this ice table? X. So we already have X. So percent ionization is equal to X over your initial concentration that was given. So in the context of this question, it's 0.00232 over 0.30 molarity. And so if I do that, so 0.3 times 100, I get that this sample is less than 1% ionized. It's 0.77% ionized. That's less than 1%. So what that means is that this reaction only goes forward about 0.5%, or like less than a percentage of these particles move over to the ionized side. That's what that means. And so since this number is a lot less than 5%, we are absolutely fine to go with the approximation. 99.9% of the time, we can approximate because we're within the realm of percent ionization. All right. So we'll pick up here on Tuesday next week. We'll move through chapter 16 slowly. I'll incorporate some review, but I do plan on finishing chapter 16 next week. Yeah.